In 1908, in a basement laboratory in the Dutch city of Leiden, a physicist was chasing the coldest temperature ever produced by a human being, colder than the Arctic, colder than outer space near a star, closing in on a limit physics says can never quite be reached. That limit is called absolute zero, about minus 273.25 degrees Celsius, the theoretical point where all thermal motion in matter simply stops. You can get close to it. Reaching it exactly may be physically impossible, but how close you could get had become one of the great competitions of the era. Through the 1800s, scientists liquefied one stubborn gas after another by cooling and compressing it. Oxygen, nitrogen, then hydrogen in 1898. Each success set a new cold record. Each one also revealed the next, colder holdout waiting in line. One gas refused to cooperate with anybody, helium. Its boiling point sat far colder than anything liquefied before it. A final, frustrating holdout standing between physicists and the true edge of what temperature could do. Here's a nice irony. Helium was first discovered in the sun, in 1868, as an unexplained line in sunlight's spectrum, decades before anyone found it here on Earth. A gas named for the Greek sun god, hiding the whole time in our own atmosphere. The man determined to finally liquefy it was Heike Kamerlingh Onnes, a Dutch physicist at the University of Leiden. Meticulous, almost to a fault, with a lab motto that said everything about him, door meten tot weten. Through measurement to knowledge. Onnes didn't chase this in some small, cluttered lab. He built an industrial-scale cryogenics workshop, compressors, coiled copper pipe, teams of glassblowers and technicians, a genuine factory built for the sole purpose of making things cold. This apparatus took years to design and refine, and a fortune to build. There was no single eureka moment here, just relentless engineering, failed attempts, redesigns, and the patient elimination of every possible leak and flaw. Rival labs across Europe tried and failed. The physics is brutal. Helium liquefies only a few degrees above absolute zero, so any stray impurity, any tiny heat leak, ruins the whole run before it starts. On July 10, 1908, after years of preparation, Onnes' team ran the apparatus through its final cooling stage, gauges trembling, technicians watching in tense silence, everything riding on this one attempt. And then it happened, for the first time in human history, a few cubic centimeters of liquid helium, collected at the bottom of a glass vessel, at 42 Kelvin above absolute zero, roughly minus 269 degrees Celsius. Onnes has achieved something no one else on Earth could, and for now, he held a total monopoly on it, the only person alive who could produce liquid helium, and therefore the only person who could study anything at these temperatures at all. Leiden became, quite literally, the coldest place on Earth, and stayed that way for decades. Other laboratories simply couldn't get liquid helium of their own. If you wanted to work at these temperatures, you came to Leiden. With liquid helium finally in hand, Onnes could chill almost anything down near absolute zero, and that raised an obvious next question. What happens to ordinary materials, ordinary physics, way down there? He picked a deceptively simple target. Electrical resistance in metals. Every wire resists the flow of current somewhat. Electrons collide with the jostling atoms of the metal, and some of that electrical energy is lost as heat. It was already well known that resistance drops as a metal cools. Colder atoms jostle less, so electrons collide with them less often. But how far does that drop go? Does it ever actually reach zero? This wasn't idle curiosity. The answer would say something deep about the very nature of matter and electricity, right at the edge of stillness itself, a place no one had ever been able to actually visit before. Nobody could test this before because nobody else had liquid helium. Onnes had built, almost as a side effect of his real ambition, the only machine on the planet capable of even asking the question. So, a new experiment began in that basement, colder, more careful, and destined to be far more contested than anyone in the room expected. What actually happens to resistance as a metal falls all the way toward absolute zero. Before we see what actually happened, it's worth meeting the three competing predictions physicists genuinely held in 1911 about resistance near absolute zero. All three were respected. All three were completely different. And nobody could test any of them yet. James Dewar, the chemist who liquefied hydrogen, guessed the simplest answer: resistance would just keep smoothly falling, all the way to zero, as temperature fell toward zero. A clean curve, no surprises, no drama. Lord Kelvin guessed the exact opposite. As temperature dropped, he reasoned, electrons would essentially freeze onto their atoms, unable to move at all, and resistance would shoot upward, toward infinity. A dead, frozen metal. A third, more cautious view, built on Mattheson's rule, said resistance would simply level off at some small, unglamorous, non-zero floor set by leftover impurities in the metal, never quite reaching zero no matter how cold you got. Three respected scientists, Three totally different shapes for the same simple graph, and absolutely no way to settle it. Until somebody actually had liquid helium cold enough to run the real test. To settle it, Onnes needed the purest possible sample. He chose an unusual metal for the job, mercury, liquid at room temperature, but a solid wire once it's cold enough. Mercury can be distilled and redistilled to a purity that's almost impossible with ordinary solid metals because liquids purify so cleanly. Fewer impurities meant a cleaner, fairer test of the actual physics, not just leftover contamination. The team froze the purified mercury into a thin, U-shaped glass capillary tube, a thread-like solid wire of nearly pure metal, carefully wired up so its resistance could be measured with precision. Running the actual measurements fell largely to Onnes's brilliant assistant, Gilles Holst, working alongside technicians Cornelis Dorsman and Gerrit Flim, a real team effort behind the one name history remembers. On April 8, 1911, they began cooling the mercury capillary, bathing it in liquid helium, watching the resistance meter as the temperature crept down toward just a few degrees above absolute zero. At first, nothing shocking. Exactly what everyone expected. As the mercury got colder, its resistance dropped smoothly and steadily. Duer's simple curve holding up just fine, so far. The real question still hung in the room. Would it flatten out the way Matthew Essen predicted? Would it turn and rocket upward the way Kelvin predicted? Or just keep falling all the way to nothing? Nobody in that Leiden basement realized they were minutes away from an answer that matched none of the three guesses at all. A fourth possibility nobody had even thought to propose. The temperature ticked down to 4.3 Kelvin, then 4.2. And the needle on the resistance meter was about to do something that would quietly rewrite the textbooks of physics. Let's watch exactly what the data showed that afternoon, because what happened next wasn't a smooth curve easing to zero, a rise toward infinity, or a tidy plateau. It was something else entirely. Here is the actual measurement, the founding data of an entire field, mercury's electrical resistance, plotted against temperature, dropping smoothly, and then collapsing to exactly zero at 4.2 Kelvin, a sheer cliff off the chart. At 421 Kelvin, the resistance was still small but measurable, still behaving more or less like the smoothest of the three guesses. Then, across a whisper of a temperature change, at 420 Kelvin, the resistance didn't ease down gently. It didn't level off, it fell off a cliff, plunging to a value too small for any instrument in that lab to detect at all. Onnes's own notebook that afternoon records it in a single blunt phrase, in Dutch, quick nagenoeg nul. Mercury's resistance, next to nothing. Not very low. Not approaching a limit. As far as anyone in that room could measure, with the best instruments in the world, the resistance had become precisely zero. The team checked for a short circuit. They rechecked the wiring, the meters, every assumption they'd made. Nothing was broken. The mercury really had simply stopped resisting the current, all at once. This matched none of the three respective predictions. Not Duer's smooth zero, not Kelvin's rise to infinity, not Mathiassen's plateau. It was a sudden, total, all-or-nothing transition, a phenomenon nobody had guessed at all. Onnes published the finding carefully and precisely. Mercury, he wrote, had passed into a new state, which on account of its extraordinary electrical properties may be called the superconductive state. He needed a word for it, and tried superconductivity first, before settling on the term we still use today, superconductivity, a metal, at a precise cold temperature, with zero electrical resistance at all. To prove this wasn't some measurement quirk, Onnes tried something bolder. Start a current flowing in a closed loop of superconducting wire, disconnect the battery entirely, and simply watch what happens next. In an ordinary wire, that current dies out in a fraction of a second, its energy eaten by resistance. In the superconducting loop, the current just kept going, no battery, and, as far as anyone could tell, no end. Experiments like this, repeated for years afterward, found no measurable decay in the current at all. A current that, by every practical test, could circle a loop of wire forever with nothing driving it. Onnes had built the only laboratory on Earth equipped to even ask this question, and found an answer stranger and more absolute than any of the three respected guesses that came before it. In 1913, Onnes won the Nobel Prize in Physics, officially for his investigations on the properties of matter at low temperatures, honoring the liquid helium and the cold itself, the tool that had made this whole discovery possible. And here was the catch that would haunt physics for decades. Onnes had discovered precisely what happened. He had absolutely no idea why it happened, none at all. Classical physics simply had nothing to say about a metal that stopped resisting current entirely, all at once, at one precise temperature. The effect was undeniably real. Superconductivity turned out not to be unique to mercury either. Lead, tin, and other metals soon showed the exact same cliff, each one dropping to zero resistance at its own particular critical temperature. A phenomenon with no explanation is still very much worth chasing, though, and the mystery of superconductivity would go on to consume physicists for the next 46 years. So, the discovery stood alone for a generation, undeniable, tantalizingly useful, and completely unexplained, a genuine working miracle that nobody on Earth could yet account for. For 22 years, superconductivity just sat there as an unexplained fact of nature, until 1933, when two German physicists found something that made the whole mystery even stranger. Walther Meissner and Robert Ochsenfeld cooled a superconductor while it sat inside a magnetic field and watched the field itself, and it did something no ordinary perfect conductor should ever be able to do. The magnetic field was pushed completely out of the material, actively expelled, as if the superconductor simply refused to let it in at all. This became known as the Meissner effect. This mattered enormously. A merely perfect conductor with zero resistance alone would just trap whatever field happened to already be inside it as it cooled. A true superconductor actively shoves that field back out. That meant superconductivity wasn't simply resistance equals zero, it was an entirely new state of matter, with its own rules, a genuine phase transition, the way liquid water turns into solid ice. One vivid, almost magical consequence of the Meissner effect: a small magnet can be made to float, hovering perfectly still above a superconductor, suspended entirely by the field is forbidden from entering. By the 1930s, physicists had two deep mysteries stacked on top of one another. Why does resistance vanish entirely, and why does the material actively expel magnetism? Neither one yet had a real explanation. Solving it required the full machinery of quantum mechanics, a theory capable of describing how billions of electrons behave together, collectively, inside a cold metal lattice. That kind of theory simply didn't exist yet. It took until 1957, 46 years after Onnes's cliff, for three American physicists, John Bardeen, Leon Cooper, and John Robert Schrieffer, to finally crack it at the University of Illinois. Their theory is called BCS, after their three initials, and its central idea is almost poetic. At low enough temperatures, electrons, which normally repel each other fiercely, team up into bound pairs. Here's the trick. An electron moving through a metal lattice slightly tugs the surrounding atoms toward it as it passes. That tiny distortion can, in turn, gently attract a second electron from some distance away. The result is a bound duo physicists now call a Cooper pair, and below the critical temperature, nearly all the free electrons in the metal lock into pairs exactly like this, all at once. Individually, an electron gets knocked around by the lattice, losing energy as heat. That's ordinary resistance. Cooper pairs behave very differently. They glide through the same lattice together, essentially undisturbed. It takes a certain minimum energy to break a Cooper pair apart. Below the critical temperature, there simply isn't enough random thermal jostling around to supply that energy, so the pairs just keep flowing indefinitely. Picture a stream of paired electrons flowing through a wire like dancers moving in perfect step, a coordinated quantum dance too well organized for the ordinary chaos of the lattice to disrupt. BCS theory explained the Meissner effect too. The paired electrons collectively resist any change to a magnetic field trying to pass through them, actively pushing that field back out of the material. In 1972, Bardeen, Cooper, and Schrieffer won the Nobel Prize in Physics for BCS theory. For Bardeen, it was remarkably his second Nobel Prize in Physics, an extraordinary, almost unheard of achievement. So the arc finally closes, 1911, an unexplained cliff. 1933, an even stranger companion mystery. 1957, at last, a complete quantum theory that explains both of them together. It's worth pausing on that timeline, 46 years between we found this and we finally understand why. Real science is often exactly that slow, that patient, that stubborn, and that's completely normal. And once physicists finally understood why superconductivity worked, they could ask a much more exciting practical question: how much warmer could they possibly make it happen? Because so far, every known superconductor required liquid helium, rare, expensive, and difficult to produce, chilling everything down to within a few degrees of absolute zero just to make it work at all. If superconductivity could ever be coaxed into working at higher, cheaper, easier temperatures, it wouldn't just stay a laboratory curiosity. It could genuinely change engineering itself. That single practical hope, push the critical temperature higher and higher again, would go on to drive one of the strangest, most surprising research chases in the whole history of physics. Let's watch how far that chase has actually come. Because the climb from Onnes's 4.2 Kelvin cliff to today is one of the great, ongoing graphs in modern physics. Physicists first hunted for higher critical temperature simple metals and alloys. Niobium held up better than mercury, superconducting up to about 93 Kelvin, still bitterly cold but a genuine step up. Alloys did better still. Niobium titanium and niobium tin pushed critical temperatures up toward 10 and 18 Kelvin, cold enough to matter for engineering and warm enough to actually build real magnets from. But for decades, every single known superconductor still needed liquid helium. And liquid helium is rare, expensive, and awkward. Nothing at all like the abundant, cheap gas we call nitrogen. Liquid nitrogen, by contrast, boils at 77 Kelvin, about minus 196 degrees Celsius, and can be made cheaply almost anywhere straight out of ordinary air. If superconductivity could survive above 77 Kelvin, everything would change. For roughly 75 years, nobody found a material that came anywhere close. Most physicists assumed brittle, non-metallic ceramics were the very last place you'd ever go looking for, a superconductor. Then, in 1986, two IBM researchers in Zurich, Georg Bednorz and Alex Muller, tried something almost nobody expected to work at all, a ceramic copper oxide compound laced with lanthanum and barium. It superconducted at 35 Kelvin, no record-shattering warmth on its own, but far, far higher than anyone thought a ceramic like this should ever manage. The old assumed rules had just quietly broken. Labs worldwide scrambled to push the same family of materials further, and within about a year, Bednorz and Mueller won the 1987 Nobel Prize in Physics, the fastest turnaround from discovery to Nobel in the prize's history. Here's the whole climb laid out at once: the critical temperature of superconductors, rising across more than a century, mercury's 4.2 Kelvin in 1911, niobium, the 1986 ceramic leap, and everything that followed. The real shock, though, came within months. A team led by Paul Chu and collaborators found yttrium barium copper oxide, YbCO, superconducting at roughly 92 Kelvin. 92 Kelvin doesn't sound warm, it's still around minus 181 degrees Celsius, but it crossed a magic line. It was above the 77 Kelvin boiling point of liquid nitrogen. Suddenly, sheep cooling actually worked. A superconductor, you could chill with liquid nitrogen, instead of scarce liquid helium, was a completely different, vastly more practical animal. And physicists everywhere sensed the ceiling could keep rising further still. It kept rising. In 1993, a mercury-based cuprate ceramic reached about 133 Kelvin at ordinary pressure, and later variants of the same family edged the ambient pressure record up toward roughly 138 Kelvin. Then researchers tried something entirely different, crushing hydrogen-rich compounds under pressures rivaling the center of the Earth. In 2015, compressed hydrogen sulfide superconducted at 2003 Kelvin, colder than a hard winter, but astonishing for a hydride. In 2019, lanthanum hydride, squeezed to roughly 170 gigapascals, over 1 million times atmospheric pressure, superconducted at about 250 Kelvin, minus 23 degrees Celsius. Genuinely, tantalizingly close to a chilly room. That's real progress, but it comes with an honest asterisk. Those hydride results only work under crushing, diamond anvil pressures. Nothing remotely like a room you or I could ever stand inside. And it's worth being candid about the field's growing pains. Two headline claims of genuine room temperature superconductivity at low pressure in 2020 and 2023 were both retracted by the journal Nature after serious concerns about the underlying data. That's not a scandal that discredits the whole field. It's science doing exactly what it's supposed to do, scrutinizing extraordinary claims hard and correcting itself in public when they don't survive that scrutiny. The genuine, verified climb is already staggering on its own, from 4.2 Kelvin in 1911 to over 130 Kelvin at ordinary pressure to past 250 Kelvin under extreme pressure, a real, checkable, century-long achievement. And this was never just an abstract physics chase. Superconducting niobium titanium magnets are the beating heart of every MRI machine, letting doctors see clearly inside a living body without a single incision. The same superconducting magnets bend particle beams around the Large Hadron Collider's 27-kilometer ring. Without them, that ring would need to be nearly 5 times longer. And in Japan, they lift entire trains off their rails to glide above 500 kilometers an hour. From a frost-rimmed basement in Leiden to the scanner, the collider, and the train. That's the reach of one measurement in 1911. Thanks for being awake and curious with me today. Share this with someone who thought zero resistance sounded boring. Until next time, keep looking closely at the cold, quiet corners of physics, because that's often exactly where the strangest, most useful discoveries are hiding. Stay curious.